Okay. So good evening, guys. So please type in the chat box, is the audio and video clear to all of you? Just a second. I think there was slight. Yeah. Okay, fine. So please type in the chat box, is the audio and video clear to each of you? So please confirm quickly, then we can start the session fast. Hi, good evening, Ashwini. Please type in the chat box, is the audio and video fine to all of you? Okay, so it's fine, right? Yeah, good. So let's start the session basically. So today we are in continuation with this 7 p.m. series, and in today's lecture we are going to have lecture number 3 in this single variable calculus. Okay, and majoritarily we are going to focus on this principles of basically fundamental theorems of integration, and also some nice important properties of definite integrals, of course. Okay, just a minute, some pop-up coming. Okay, fine. Okay, so yeah, good evening, Sakshi. So basically we are going to start in today's class the fundamental theorems of integration and also some nice properties of definite integrals, okay, which makes you basically calculate integrals very fast actually. Okay, so we'll see that. And of course, before that, this is the Telegram channel for the updates on the English channel, and this is the personal Telegram channel of mine, so you can just scan the codes and you stay in update with all the relevant information that also. Okay, and please install this Unity platform so that you can have all the track of your doubts at a single point and all the track of your nice points at a single location, of course. Okay, and clearly before start typing your doubt, if you put exclamation and doubt, and then if you type your doubt, then that doubt will be stored at a given place in the Unity, and all your track will be there at a particular place. Okay, so that all your polls, each and everything can be decided nicely. And then in today's lecture, so basically in the last lecture we were talking about the concept of maxima and minima, correct? So we have talked about the concept of maxima and minima, and we have seen the result, like if for example y is equal to f of x, then the procedure is to calculate stationary points, and once you get stationary points, the number of stationary points again depend upon the number of depends upon this function f of x. Like we can see, long time no see. It's okay, Alex, I remember you, so just follow up the sessions. Okay, so stationary point, so basically if you calculate the derivative and equate it to 0, then ultimately you'll get a stationary point. Okay, and number of stationary points you'll have for a function purely depends on the function, the degree of the function. And in last class we have seen, like in few cases where trigonometric equations or the transcendental equations come up, we have infinite number of stationary points actually. Okay, so the stationary points purely depend upon this function f of x. And now once you get this stationary point, then ultimately if you calculate f double dash of x, if this is 0, then ultimately f of x has maximum at x is equal to x naught. So this has maximum at x equal to x naught, and maximum value is of course f of x naught. Maximum value is f of x naught, of course. Okay, and f double dash of x naught being positive, so this implies f of x has minimum at x is equal to x naught. And what's the minimum value? Of course, so this is x naught, and minimum value is f of x naught in this case. Minimum value is f of x naught. And what if the second derivative is also 0? The first derivative is 0, of course, and second derivative is also 0. This implies f of x or basically x naught is critical point actually. Okay, so x naught is a critical point. And if you want to check whether this critical point is a point of inflection or not, just check for the neighborhood values of the function. So if f of x naught minus and f of x naught plus are having, basically if one of them is more than f of x naught and the other is less than f of x naught, then ultimately you will have a saddle, like you have seen in the case of f of x is equal to x cube. Okay, so this is the classical procedure that I have given you, and we have worked out few questions, and really we have worked out the other questions as well where this classical procedure fails, of course, or basically the second derivative test actually fails. Okay, so these are the things that I have covered basically in a nutshell in the till the last lecture. So are you all comfortable till this point? So please type in the chat box. So please type in the chat box, are you all clear till this point? Everyone, Ashwini, Sakshi, Sagnika, Shravan, Alex, Ajit, every one of you first. Ajit, so in basic calculus, what is the difference between open bracket and closed bracket? So basically if you see, if you have something like this, let's say if I let x belongs to this, this implies a less than x less than or equal to b. Okay, so if you have a closed bracket, this value is included in the limits, and if you have open bracket, this value is not included. Okay, so that's the simple idea. Now let's go to today's topics. So we are going to look at fundamental theorems of integration and also properties of definite integrals. But before I start these topics, I want to give you one question and I want to conduct a poll of course. So solve this question. The real values, for real values of x, the minimum value of the function e power x plus e power minus x is dash. Okay, so I'm giving you 120 seconds to solve this integer type and start the poll. So the function is e power x plus e power minus x. Come on, calculate it quickly, because if you have revised, you would have been fast with these calculations. Come on, do it quick. Y is equal to f of x, which is e power x plus e power minus x. Hi, good evening, Vijay. Come on, guys, just follow up and solve this. It's okay, you haven't missed many classes, only a couple of classes were done, Alex. Okay, based on Taylor series and Maxima and minima. In today's class, we'll start integration. One, maybe possible. Two, 0. Okay, so 0, 1, 2, start the sequence. 3, 4, 5. 0 is the maximum value, is the minimum value. For real values of x. So say 0, 0. Good, many of you are typing 0. Pavan, Vijay, Ashwini, Ravi. Good. Okay, so let's solve this question. It's again a nice question. So let's solve this. So f of x is equal to e power x plus e power minus x. This is what you get, of course. Okay, so it's like 2 cos hx basically. Then let's see, if you follow the classical procedure, let's say f dash of x is equal to e power x minus e power minus x. So equate it to 0. This tells you e power x is equal to e power minus x. So e power x whole square is equal to 1. So e power x is equal to 1, x is equal to 0, of course. Correct, because x is equal to log 1 to the base e, which is 0. So this is stationary point. So one and only one real stationary point. So stationary point, of course. Stationary point. Now if you calculate f double dash of x naught, so f double dash of x is equal to, if you differentiate this function once again, you will end up with again e power x plus e power minus x at x is equal to 0. If you calculate this value at x is equal to 0, it turns out to be 2, correct? Because e power 0 is 1 plus e power minus 0 is again e power 0, which is 1 plus 1, which is 2, and it is positive. So this tells you that this y is equal to e power x plus e power minus x has, since the second derivative is positive, it has minimum at x is equal to 0, of course. And what's the minimum value? Minimum value is e power 0 plus e power minus 0, which is equal to 2. So that's basically the minimum value. So 2 is the minimum value of this function. Okay, in neighborhood of x, x belongs in neighborhood x belongs to a minus delta comma a plus delta. That means a minus delta comma a plus delta are not neighborhoods of a. Is it right, sir? Yeah, of course. Okay, so let's see. This is the classical way to solve this question, or there is one more method which you can do actually here. Okay, since we are worrying about the real calculus, okay, we are in the real planes. So do you know something? If a comma b are two positive attributes or two positive real numbers, let's say two positive real numbers, Do you know something that arithmetic mean is always greater than or equal to geometric mean? Do you know this property? Like if you take two numbers a comma b, then a plus b by 2 is always greater than or equal to square root of ab. Do you all know this? Means something like a plus b by 2, if a comma b are the attributes, this is greater than or equal to square root of ab, of course. Yes, can I do this? Yeah. Now if you know this, then this function can also be done very easily. If you take these two functions, e power x and e power minus x, e power x and e power minus x, will they be always positive? Correct, because whatever the value of x you place there, e power x and e power minus x will never go to negative actually. Okay, so therefore since e power x comma e power minus x is greater than 0 for all x belongs to real numbers, this implies e power x plus e power minus x by 2 is greater than or equal to square root of e power x into e power minus x. Please make a note, for this to happen, ultimately these two should be positive. Okay, otherwise when you are taking square root, it ends up in complex plane, which is again a bit difficult, so which you cannot do. Obviously you cannot prove this. So here it is a positive, here it's a positive, and obviously these two are also positive. Okay, so you can apply this. So if you apply this, then ultimately these two cancels. So this tells you e power x plus e power minus x is always greater than or equal to, if you put to the other side, this is the inequality that you have. Okay, so this is greater than or equal to 2, of course. So which even eventually the classical procedure of maxima and minima also gives you the same thing. The answer is more than 2, of course, which is of course here the same thing. E power x plus e power minus x is greater than or equal to 2. If this value is always greater than or equal to 2, then the minimum value that this function can go is 2, which we had here. Okay, so that's the case. Fine. So please type in the chat box. Is this clear to all of you? Okay. But this can happen only when these two are positives. Okay, which clearly happens in this case. Okay, otherwise you cannot do that. Then I'll give you one more question. So the correct answer is of course 2. Let's see how many of you have entered. Throw it, man. It's not throwing. So let's see. Pranav, Sagnika, Ashwini, you guys have answered correct. Nice. Acha, okay. Fine. So let's see. Let us solve this question. The minimum value of the function x cube minus 3x square minus 24x plus 100 in the interval minus 3 comma 3 is dash. Okay, so again I'm giving you some poll. They have given you the limits in this case. So let's see how many of you do this. So again, yeah, maybe 120 seconds is good enough, or 150. Let's, okay, 120 is fine. Do Vijay, Ajit, Sagnika, Pranav, Ed, Alex, Pavan, every one of you. Please solve this question quickly. The minimum value of this function in this interval minus 3 comma 3. Is there any conditions where we apply the formula and where we can't? No, in general you can check for any function the second derivative test. Okay. The am greater than or equal to gm can happen only when the entities you put inside the square root are positive. Okay. X cube minus 3x square minus 24x plus 100, of course. Come on, solve this question quickly. Minimum value of the function f of x is given by x cube minus 3x square minus 24x plus 100 in the interval minus 3 to 3 is dash. $27 maybe. Yeah, whatever you want you can enter in the chat box. 27 minus 27, then 28. Okay. See, accuracy is really important. Okay. Could you please tell some examples of finite valued functions other than sine and cos? Many. Like if you take the intervals, okay, like cos 2x, sine 2x, then integer part x is generally finite within a given domain. You can. Okay. So let's see. Then, if you solve this function. So let's see, given f of x is equal to x cube minus 3x square minus 24x plus 100, of course. Okay, so what is f dash of x? So 3x square minus 6x minus 24. If you equate this to 0 in this case, you will actually get x square minus 2x minus 8 is equal to 0, of course, correct? So if x square minus 2x minus 8 is equal to 0, this gives you x is equal to 4 comma minus 2. So these are the stationary points here. Stationary points. Okay, so these are the stationary points. Now let's see if these are the stationary points. Then if you calculate f double dash of x, this is actually f dash of x. So if you calculate f double dash of x, it gives you 6x minus 6. Okay, so which is 6 times of x minus 1, obviously 6 times of x minus 1. Now let's see if you replace these values here. Okay, so if you replace, correct, 4 comma minus 2 is the answer, right? 4 plus 4 into minus 2 and 4 into minus 2 is minus 8. Okay, so I hope x square minus 2x minus 8 is equal to 0. I think this is the actual value, 3x square minus 6x minus 24. So if you cancel a 3, x square minus 2x minus 8, so ultimately roots of 4 comma minus 2. Then okay, so f double dash of 4 actually. So if you keep this 4 minus 1, which is positive, then f double dash of minus 2. So this is 6 into minus 2 minus 1, which is negative clearly here. Now let's see, and also the interval is given. Whenever they give you the interval, please check the values of the function at these stationary points, like 4 comma minus 2 are the stationary points. And also when they give you the interval, this comes in the concept of basically local maxima or local minima, of course. Okay, so let's observe what do we get if you calculate f of, so this implies, let's check carefully, this implies f of x, if you check these points, has this second derivative is positive, has maximum at x is equal to minus 2 comma minimum at x is equal to 4. Okay, at x is equal to 4. You understand this? So this is the value that tells you the function has maximum at x equal to minus 2, because ultimately second derivative is negative and first derivative is 0, of course, and clearly minimum at x equal to 4, because at x equal to 4 first derivative is 0 and second derivative is positive, of course. But so many of you are very tempted to write, you calculate f of 4, because that's the minimum value, and here they're asking you for the minimum. So if you calculate f of 4 cube minus 3 times of 4 square minus 24 times of 4 plus 100 actually. So if you simplify this, let's see, 64 minus 3 16s 48 minus this is again 96, okay, plus 100, of course. Okay, so if you simplify these values, 164 minus 6 plus 8 14, 1 4 plus 9 13, and this is 14. So this value is coming out to be 20. Yes or no? Correct? This value is coming out to be 20. 2 f of 4 is coming out to be 20. Okay, so please type in the chat box. Is this clear to all of you? First of all, here till this point it's 20. Okay, but in the question they asked you the minimum value of this function in this interval. Okay, is 4 belongs to minus 3 comma 3. Is 4 lying in this interval? Is 4 lying in this interval minus 3 to 3? No, obviously, correct? So of course the function has the global minimum, means the total, the absolute minimum of the function is present at x equal to 4, but you are not interested at the absolute minimum, but you are interested in the minimum of the function in this interval. So that's why the answer is no here. So therefore, even though this is the minimum value of the function, but this value is not the minimum in this interval. Okay, so therefore when interval is given, along with calculation of stationary points, you should also calculate f of minus 3 comma plus 3. So let's calculate f of minus 3. So f of minus 3. So let's calculate this value, f of minus 3. So what is f of minus 3? Let's see, minus 3 whole cube minus 3 into minus 3 whole square. Okay, so 3 into minus 3 whole square minus 24 times of minus 3 plus 100. So this value tells you minus 27. This is again minus 27 because this is 9. 3 9s are 27 with a minus sign, plus 72 plus 100. So 172 minus 54. This gives you 118, of course. Okay. 2. So 54 plus 118 gives you 1271. Okay. So 118. Then f of 3. What is f of 3 value? F of 3 value is like 3 cube minus 3 into 3 square minus 24 into 3 plus 100. So these two gets cancelled. Then you have this value is 100 minus 72 is 28, of course. Okay. So this is 28. Now, when they give you the interval, along with calculating the function at, I'm not calculating f of minus 2 because obviously at f of minus 2 the function would have got a maximum, okay, which the second derivative test tells you. Like if you calculate f of minus 2, let me show that the value would be definitely more than 118. Okay, so f of minus 2, if you calculate, then minus 2 whole cube minus 3 into minus 2 whole square minus 24 times of minus 2 plus 100. Okay, so this is something like minus 8, and this is around 3 4s are 12, of course, minus of minus plus 48 plus 100. So clearly you can see this is 20. So 48 minus 20 is 28, plus 100 is 128. So this 128 is definitely more than this value because we ultimately know from the second derivative test at x equal to minus 2 this function has a global maxima. Okay, now what is global maxima and global minima in general is, it's quite possible few times when you have this function x of y. So let's say if the function is something like this, okay, so which is plotted like this. Now it's possible that you get signals like this, and let's say this is the point, say for example in this case x is equal to 4, where this function has got the absolute minima of the function, the absolute minima, and how much it is? 20. Okay, so this is 20, but it's 28. Yeah, it is 20. We are talking about the absolute minimum, and what is f of 4? We have got, just a second, f of 4 is 20. Sorry, then this is the minimum. You want to make this as minimum, then absolute minimum, you are getting 28. F of 3 is basically 28. Okay, so okay, let me plot this function exactly using Desmos because fitting is again giving you some issue. So let's plot this function because I want to show you few important insights. So let's see. I'll plot this function so that you can observe some points actually. So what's the function actually? X cube minus 3x square minus 24x. X cube, let's see, x cube minus 3x square plus x cube minus 3x square minus 24x. So this value is minus 24x. Okay, so minus 24x plus 100, of course. Okay, so plus 100. Then you can see this function, if you zoom out for example, okay, so if you zoom out, this is the total minimum of this function. Okay, so it is coming out to be minus 70 somewhere, right? So just a minute, it's the function x cube minus 3x square minus 24x. It is minus 24x or plus 24x? Let's see, minus 24x. So if you put x is equal to 4, what's coming up? 4 cube minus 3 times of 4 square minus 24 times of 4 plus 100 actually. So this value, if you simplify, 64 plus 100 is 164 minus this value is total 144. So this is 20. F of 4 is coming out to be 20 actually. Okay, so f of 4 is somewhere here. You zoom in, then f of 4, 1 2 3 4. So this value is 4 somewhere, but within this interval, if you check, minimum of f of x in minus 3 comma 3 is equal to minimum of f of minus 2 comma f of minus 3, f of 3 comma f of 4, of course. Okay, so this is the values, and of course in minus 3 to 3 you don't bother about this value because that is not in this interval. Then if you simplify this, it is like minimum of f of minus 2. So what is f of minus 2? We have got f of minus 2 is 128, f of minus 3 is 118, and f of 3 is 28. So minimum of these values is actually 28. That's it. Okay, because the graph is slightly expanding. You type plus 10 where? Okay, then it's 100. Then the graph would shift slightly. So basically you can see this is the value which is 20 at x is equal to 4. Okay, I have missed a 10, so that's why it's 100. So if you see now, the minimum in this case is the finite value of the minimum. Here it's going to infinity like this. So it is at 4 value, the value is 20, but at x is equal to 3. So let's say somewhere here. So 3 is somewhere here, of course. So at 3 it is 28. So if you check the function from -3 to 3, from -3 is somewhere here to the left hand side of this x-axis. So from -3 to 3, if you check the value, it is minimum at this point, and it is 28, which is something like this. If they give you the interval along with calculation of function at stationary points, should also calculate at the limits of the interval. Okay, and you have to decide maximum or minimum accordingly what they ask in the question. Clear to all of you? Because few times it can happen, like here you can see the absolute minimum is 20 in this case, the finite minimum is 20, but this 4 x is equal to 4 is not within the interval. So we are bothered only about till this point, maybe somewhere here. So we are interested only about till this point. Okay, so 3,28 is the point where you have, we are interested only till this point, and till that point from -3 to 3 the function has a minimum of 28, of course. Okay, is this clear to all of you? When they give you interval, please check the values of the function along with the stationary points. Okay, fine. Like if you see, if I trace this part of the function, maybe I can show something like this. It started with something like this, f of -3. So let's see f of -3 value, where it is, f of -3. So what is this value? -4. So if you see, f of -3 is still up. Maybe f of -3 is somewhere still it's moving, so it's almost like an asymptote. So f of -3 is more than 100. Okay, so basically if you see, the function is something like this. Okay, but we are focused only in this part. In this part, the minimum is here, so which is 20, of course, 28, of course. Okay, and at x equal to 4 it's still dropped, but we bother only about this part of the function because -3 to 3 is only in this regime. That's why. Okay, then so basically these are the questions of maxima and minima I thought of putting today as well. So let's start the fundamental theorems of integration. Okay, so the first theorem, again, fundamental theorem of integral calculus. Of course there are many, but one gives the differentiation and integration definitions. So fundamental theorem of integral calculus, Okay, so let's see how do we calculate this fundamental theorem of how do we write this fundamental theorem of integral calculus. So let's see, if capital F of x is antiderivative of small f of x, that is basically if you want f of x, you have to differentiate this capital F of x. Okay, if small f of x is derivative of capital F of x, then ultimately capital F of x is, if you shift this operator to the other side, antiderivative of this small function f of x, and it is differentiable, and it is differentiable for all x belongs to a comma b. Then we write the antiderivative operator is written as the integral symbol. So integral a to b f of x dx. So this is written as f of b minus f of a actually here. Okay, so this is how the integral operator is defined. So basically this capital F of x is called the antiderivative. Okay, means if you want capital F of x, you have to apply something which is the inverse operation of differentiation, which is basically integration. Okay, so physically differentiation means splitting up into small portions, and integration means putting together. Okay, so normally in This word integration is heard many times. Okay, so integration of systems, integration of sensors, you come across this many times. So in general, if you see the generalized form, is integral f of x dx is equal to, or basically this integral f of x dx is equal to some capital F of x plus constant. This c is called arbitrary constant. So c is called arbitrary constant, of course. Okay, so means any value of c will definitely satisfy this, because if you take differentiation here, then d by dx of f of x is small f of x, like as usual you have seen. D by dx of integral is something which is for inverse of differentiation. So differential operator times inverse differential operator, so both operations gets cancelled. You will have f of x, of course, and when you differentiate this quantity, derivative of c is constant, derivative of c is 0, and whatever the value of c you keep, it doesn't matter, this equation is always satisfied. Okay, is this clear? Did you all understand the definition of integration? Yes or no? So please type in the chat box. Can you all get the definition of integration? Do you all understand this? Okay, yes or no? Please type in the chat box. So basically it's very simple. Like normally if you know how to differentiate, so if you apply differentiation on both sides, you'll get differentiation of capital F of x is small f of x, which I have written here. Okay, that's called the antiderivative here. Now let's see the second theorem, mean value theorem of integration. Again, I'm dealing only those theorems which are within the gate limits of syllabus. So mean value theorem of integration. Mean value theorem of integration. So as I told you, integration is basically adding up, putting things together. Then let's see, if f of x is continuous in closed a comma b and differentiable in open a comma b, then there exists at least one value of c such that c belongs to a comma b and f of c is equal to, or basically you can say f of c is equal to integral a to b f of x dx divided by b minus a, of course. Okay, so this is very important actually. So this integration is what we write. So f of c is equal to, this bracket doesn't go, I think, just a minute. Okay, so f of c is equal to integral a to b f of x dx by, can you repeat the last part? Yes, I can repeat. So here in general what I'm telling is, if you have the limits here, okay, then ultimately this difference in the value of this function is nothing but the integration of this value. Okay, I'll show you graphically what's happening. Look, so what is this mean value theorem? So basically, like in case of differentiation, we have seen at least at one point the slope of the function is equal to the slope of line connecting these 2 points. Okay, so this is the Lagrange's mean value theorem, which I have explained you. Okay, now coming to integration, what is this value? Look, let's see, if you have this function, say x-axis and y-axis, of course, so this is origin, then this is x, this is y, of course, and let's say you have some graph like this. Okay, some function, this is some function, the shape depends on this function f of x again. So let's say this is x is equal to a and this is x is equal to b, of course. Okay, so x is equal to a and x is equal to b. Now practically what integral, as long as this f of x is positive, what this integral a to b f of x dx tells you? Integral a to b f of x dx actually tells you area between y is equal to f of x and x axis between x is equal to a and x is equal to b actually. Okay, so y is equal to f of x, and x-axis between x is equal to a and x is equal to b actually here. Okay, so look, so let's plot this line very nicely. So which tells you when you are doing integration of a to b f of x, the total area what you get is basically this area. So like which, you know, because the integrating variable is x, so projected onto x-axis, this is the area you will get. Now can you tell me one thing between these points? So let's say at some point, maybe say at this point C, so let's say at this point, somewhere in between C, at least at one point, now ultimately this value is going to be f of c. Okay, because that's the function. So clearly if this is the function y equal to f of x, this is x is equal to c, then this point if projected onto y axis, you will get f of c, right? Now if you construct a rectangle, how come in this way? Look, so if you construct a rectangle here, so we construct this rectangle, then starting from here, okay, starting from here, if you construct this rectangle, so let's say, let's mark the points a, b, c and d, let's say. Okay, so if you construct this rectangle, as you move this point along a comma b, in between a comma b, this line keeps fluctuating up and down, yes or no, right? So let's say if you for example move this c towards left to here, then ultimately this point will touch this function, so this line will be actually somewhere here, this is f of c, yes. So as you keep moving this point, this line which I have drawn here in solid will keep moving up and down. At least at one point there comes a situation where this area which you are losing because of being outside the triangle is exactly same as the excess area what you are considering inside, yes or no? Please understand this carefully. As you move this point, this line keeps floating up and down, and at least at one point there comes a situation such that the area which you are losing without considering inside the rectangle is exactly same as the area which you consider excess in this case. Yeah, can I do this? Yes or no? So what is area under the rectangle? Area under the rectangle, area under this, or area of this rectangle, basically you can say area of the rectangle is equal to, so what is the area of the rectangle? Let's see. So area of the rectangle is base into height, of course. So this height is nothing but f of c actually. Okay, and what is this base length? Base is ultimately b minus a. Okay, so this is b minus a. So if you want to calculate the area of rectangle, this is f of c multiplied with b minus a, and at least there comes one situation where this area of the rectangle and this actual area under the curve both becomes equal. Okay, so therefore at least at one point, at least for one c belongs to a comma b, area of the rectangle is same as the actual area what you will get. Correct? Can I do this? Then ultimately that's what I have given. So f of c is integral a to b f of x dx by b minus a, of course. Okay, so this tells you the mean value of the function at least at one point. Okay, so they can ask you at least at one point the value of the function f of x is dash. Okay, then you can perform this and tell the value of the function at least at one point is equal to some particular value. Okay, depending on the question what they give, and this concept is used in many places. Okay, like whenever you're going to calculate the RMS value, root mean square value, in whatever the branch you see, how is the height f of c? Can you explain? Yeah, I can explain. So if this point is c, then ultimately the point where this function touches, and if you project onto y-axis, this value is going to be f of c, correct? Because this function is y is equal to f of x. So at this point, if the x coordinate is c, then the y coordinate is going to be f of c, which is obviously this height from the base. Is this clear to all of you? Please type in the chat box. Did you all understand this mean value theorem of integration? Yes or no? Please type in the chat box. Everyone. Sujay, Shravan, Pranav, Ed, Alex, Ajit. Can we make any function into rectangular shape? Yeah, that's what the basic idea, right? You can make. But the issue is it should be differentiable. Okay, that's all. Because if you want to perform integration, that function has to be differentiable in the given domain. Advanced industrial and production. Yeah, of course, you can calculate this. You'll use this mean value theorem a lot of times, like when you're calculating root mean square values, RMS values, or basically the mean average, okay, time-based average in turbulent flows. Or in anyone from mechanical here? Anyone from mechanical? Normally, if you work out a bit of Rankine cycle, then what happens is in Rankine cycle, the heat addition is a constant pressure process. Okay, so normally if you're doing a constant pressure heat addition, but if you want to compare it with a Carnot cycle, you come with something called mean temperature of heat addition, correct? So in case of mean temperature of heat addition, what you'll do is the similar story. So here you have temperature versus entropy plot. So you have temperature versus specific entropy, let's say, if you're dealing with small amount of heats. Okay, so T and S. So let's say you start one function here. So let's say this is your process of heat addition. Okay, then ultimately, you know, del Q can be written as T times, or del Q, let's say small del Q, let's say. So del Q is equal to T times ds. Okay, and for a small interval is TDS. So if you want the total heat interaction per kg in this complete domain, then this implies Q122 is equal to integral 1 to 2 TDS is what you will do, correct? Because ultimately Q12 is actually equal to integral del Q, of course. Okay, so integral del Q, and this gives you integral 1 to 2 TDS, of course, in this case. Okay, but if you observe carefully, you can construct in general, so you can construct a plot in such a way that it's a rough sketch again. So you can construct a plot in such a way that this complete heat is assumed to be supplied at one constant temperature, and this is called the mean temperature of heat addition. Okay, so if you write this as S1 and this is S2 on this entropy axis, so ultimately this can be written as Tm into S2 minus S1 gives the heat addition, and this is equal to integral 1 to 2 TdS. So what is Tm? Obviously mean temperature of heat addition is integral 1 to 2 TdS by S2 minus S1, which is exactly this. Okay, fine. So basically you keep, there are a lot of applications. Okay, like when you are calculating the mean uniform pressure acting on the surface of a disk or something, again you will come up with these values where you divide the pressure into area divided by area, which gives you the mean pressure acting on the disk, or basically the disk is, in the case of disk clutches and all, the mean pressure, uniform wear, uniform tear, in all these conditions you do this. Okay, so just again a bit of idea, but the crux is actually this. Okay, fine. So let's go to one last theorem before we go for some numericals. We deal with something called Newton-Leibniz rule. Newton-Leibniz rule. Of course, in single variable, we are talking in single variables as of now. So Newton-Leibniz rule. So let's see, if phi of x comma psi of x are differentiable functions, okay, so these are differentiable functions, then d by dx of integral of f of x dx, but this limits on the integral need not be always constants. Okay, define electric polarization, no idea to be frank. Okay, but I think the charge is getting separated. Clear? So let's see, d by dx of integral f of x dx, and if you simplify this integral f of x dx, it's not necessary that always you have the values on this limits on this integral being constants. Okay, the values on this integral need not be constants always. So in such case, you can have this functions phi of x to psi of x. Okay, so phi of x to psi of x, and if you differentiate this here, the integration or the differentiation of an integral when the limits are not constants, okay, they are actually some functions of x. So that can be written as the composite of phi of x into psi dash of x minus f of phi of x into phi dash of x. Okay, and in some cases what happens, one limit would be a variable and one limit would be a constant in such case. So let's say for example, if psi of x is constant, then this psi dash of x would be 0. Okay, and if for example phi of x is constant, then phi dash of x would be 0 because d by dx of a constant will be 0. Okay, so depending upon these two being functions, this is how we evaluate the integral. Okay, and this is actually called the Newton-Leibniz rule, of course. So derivative of an integral with non-constant with basically variable limits. Okay, so this is something like derivative of an integral with variable limits. So normally you can see this is in case of single variable. When I talk about multivariable calculus, I'll also give you the multivariable Newton-Leibniz rule, which involves this being a function of x comma alpha. Actually alpha could be some other variable again. So right now this is the way to calculate this. So now you know this d by dx of an integral with a difference limits. So I'd like to give you one question, so please solve this question. And you know, normally when a limit gives you a 0 by 0 form, you can apply L'Hospital's rule. So let's do that. Okay, so let's see, calculate this question and tell me the answer. I have given you options as well this time. So in the previous case it is 28, of course the correct answer. So some of you have done it. Kanav, Sagnika, nice. Solve this question, single choice. Maybe again 150 seconds is what I am giving. No, 120 is fine. Yeah, solve. Solve this question quickly. So should I solve all 38 years of PYQs, get mechanical? No need. Yeah, it's okay. You can solve from 2008. That's good enough. Okay, 16 years or 15 years, good, more than enough. 2009 also be good. Fine. Okay. I have made a video on this channel like which branch students should solve which PYQs of maths. Okay, like it's not like, because maths is common and let's say you want to, let's say, practice questions of single variable calculus, then it's not possible for you to solve all 30 papers maths questions. Okay, then so like which branch questions you can solve, I have made a video on this channel again, so please once go through that in your free time. Solve this. B, D, okay, infinity, 0, good. So let's solve this question. First of all, it's a nice question again. Solution: given the function g of x is continuous and of course at 0 its derivative is existing, it is 2. So z of 0 is equal to 0 and z dash of 0 is equal to 2 actually. Okay, so let's calculate this limit. Limit x tends to 0, x tends to 0, integral 0 to g of x 2t by x dt. Okay, now tell me one thing, this integration, in this integration, let's say if you want to integrate, what is the integrating variable? Can anyone tell me? In this integration, what is the integrating variable, t or x? What is the integrating variable, t or x? Come on, tell me. T, correct? How do you know it is T? Because the differential is with respect to T. Okay. Now, if this integration is with respect to T, and if the integrating variable is T, can I take this X out of this integration? Yes. How many marks questions comes in gate mechanical based on previous year concept? In any gate paper in general, if you just solve PYQs thoroughly, if you have in hand all PYQs, and if you know the concepts very nicely, you will easily end up with minimum 65 marks. It's guaranteed. And if you get 65 marks in mechanical, the situation is such a way that your rank would be below 100 or 150. Okay, no issues. So if this integrating variable is with respect to T, then I can take this X out of the integration, which means this is the integrating variable. Integrating variable, of course. Okay. So if this is the integrating variable, then this value is limit x tends to 0. Can I write this as 0 to g of x 2t dt divided by x? Because if I take this x out, it's like 1 by x into this. So this is the value 0 g of x 2t dt by x. Now if you put x is equal to 0, what happens? Let's see. At x is equal to 0, this limit is equal to integral 0 to z of 0 2t dt by 0. Now tell me one thing, the value of z of 0 is given as 0. So if this is equal to 0, if you do any definite integral, if this lower limit and upper limit are same, then what would be the value of this integration? Come on, please tell me. If the lower limit and upper limit is same, means in general, in this fundamental theorems, you can see in this fundamental theorem, if these two limits are same, then ultimately these two values are same. So f of a minus f of a, what would be the answer? Please tell me. In indefinite integral, if the lower limit and the upper limit are same, then what would be the value? Then what is the value? Please tell me. 0, right? So this numerator will also give 0 in this case, and denominator is also 0. So this is an indeterminate form. Indeterminate form actually. Okay. So this is indeterminate form. Clear? Are you all convinced that this, if you put x is equal to 0 directly in this integration, it gives you a form of 0 by 0? Yes or no? Please type in the chat box. Fast a bit. If you put x equal to 0, can you all convince yourself that this gives you a 0 by 0 form actually? Yeah? Yes? Now, if this is 0 by 0 form, then let's see. Applying L-Hospital rule. Applying L-Hospital rule. So if you apply L-Hospital rule, then this implies limit x tends to 0, integral z to z of x 2t dt by x. Okay, so this is what you have. So this is equal to limit x tends to 0 d by dx of this integral 0 to g of x 2t dt by d by dx of x. Okay, so I have told you how to basically apply the L-Hospital rule in the single variable part. In the first part, basically 1.0 lectures. Now let's see, this is 1 ultimately. Okay, and to calculate this, now you have the Newton-Leibniz rule. Okay, also this is t dt. Instead of t dt, can I write any other variable if I want? I can write this as limit x tends to 0, x tends to 0, d by dx of integral 0 to g of x. Since this is just a variable of integration, I can keep whatever the variable I want. So 2x dx is what I can replace. Okay, because you can see in general, integral 2x dx or basically integral 2t dt, they give the same things when you have the same finite limits. Yes or no? If you have a finite limits here in these two places, then this integration and this integration gives you the same value. Okay, because it's just a matter of variable of integration. That's it. Okay, so now if you integrate this, if you differentiate this, what you will get? Limit x tends to 0, then derivative of this function, so 2 times in place of x you have to replace with g of x, it's a composite function, into the derivative of this function, which is the numerator, which is g dash of x, of course. Okay, so g dash of x minus, when you keep 0, ultimately the function value is 0. So this tells you when you replace x is equal to 0, 2 into g of 0 into g dash of 0 is what you get. So 2 times, what is g of 0? G of 0 is 0, of course, in this case. Just a minute, did we make any mess here? Just check. Integration 0 to g of x 2t dt, right? 2, it's coming out to be 2t dt in this case. Okay, so g dash of 0. So what is g dash of 0? It is 2 in this case. Okay, so g dash of 0 is equal to 2. So this final answer is going out to be 0 in this. Yes, can you check this? D by dx of integral 0 to g of x 2t dt. So it's like 2 times g of x into that inner derivative of that is g dash of x minus 0. So ultimately 2 into g of 0 into g dash of 0, which gives you 0, because this g of 0 is again still coming in this case. Okay, fine. So please type in the chat box, is this clear to all of you? Yes or no? Please check it up. Everyone, all of you, please type in the chat box, is this clear to each and everyone? Okay, because here the integrating variable is x, of course. Okay, so if x is tending to 0, then ultimately it's giving you a 0 by 0 form. So if you apply L'Hospital rule to this function, limit x tends to 0, 0 to g of x 2t dt, of course, then if you now you have seen that if you put x equal to 0, this is g of 0, so 0 to 0, this complete numerator is 0 and denominator is also 0. So if you apply L'Hospital rule, limit x tends to 0, d by dx of this part divided by d by dx of this function. So d by dx of this is 1, so it doesn't matter, and the derivative of an integral using Newton-Leibniz rule will give you this. So if you apply the Newton-Leibniz rule, this limit x tends to 0 stay as it is, d by dx of this complete function. So 2 into, so this is actually a composite function, so 2 times of g of x into, so it is x, so this x can be just replaced with g of x in this case. So g of x into g dash of x, which is this derivative, minus when you keep 0, it is almost 0. So 2 into g of 0, when you put x is equal to 0, 2 times g of 0 into g dash of 0. This value is 0 and this is 2. So 2 into 0 into 2 is 0 actually. Okay, that's it. So 0 is the actual answer in this case. Fine. Okay. So all of you, please type in the chat box. Is this understandable to all? Normally these kind of questions, they come very rare, but generally if they come, you should be in a situation to solve them. Okay, so let's see. So before going for more questions, let's properties of definite integrals, let us see some standard integrals which are helpful to you. Okay, so some standard integrals which are generally helpful in day-to-day life. Some standard integrals. Okay, so the first is, of course, let's start with the algebraic functions. So d by dx of x power n is equal to, some standard integrals. So integral x power n dx is equal to x power n plus 1 by n plus 1, and in general for n not equal to 1. Okay, n should not be equal to minus 1 actually, because if n is equal to minus 1, it gives you again division with 0, which is not defined. Okay, then what is the case if n equal to 1, n equal to minus 1? This becomes 1 by x dx, which is log mod x to the base e plus constant. Okay, so this is plus constant, log mod x to the base e plus constant. So integral of 1 by x is log mod x to the base e plus constant. Okay, and third, so let's say integral sin x dx is minus cos x plus c, because I hope all of you know these things. If you just differentiate the right hand side, you'll get the left hand side. Okay, then 4, integral cos x dx is sin x plus constant. Then 5, integral, if you have f dash of x by f of x dx, this is always equal to log mod f of x to the base e plus constant. Okay, because you can clearly see if you differentiate this log mod x, log mod f of x, okay, so d by dx of log mod f of x to the base e, if you differentiate this function, then what you get, derivative of log is 1 by mod f of x is what you'll get into the derivative of mod function. So the derivative of mod function I have given you, differentiation of mod f of x by f of x. You remember derivative d by dx of mod x I have given you as mod x by x, which is 1 if x is greater than 0, and sorry, it's not differentiable at x equal to 0, and minus 1 if x is negative. Okay, so in general the derivative of mod x is actually mod x by x. So similarly, if you have this mod of some function, mod of that function divided by the actual function itself into the function inside the modulus is f of x, so the inner derivative of that is f dash of x actually. Okay, so this 1 by mod f of x corresponds to the log, and this mod of f of x by f of x corresponds to this mod function, and the function inside the modulus is f of x, so the inner derivative is f dash of x. So if you simplify, of course f of x is not 0, f denominator cannot be 0, so if you cancel these things, it gives you f dash of x by f of x actually in this case. Okay, so therefore the derivative of this is this. So ultimately integration of this is actually log mod f of x plus constant. Okay, so is this clear to all of you? Please type in the chat box. Is this fine to each and every one of you? Okay, so that's why I'm just giving you this expression. So let's see next, sixth. So obviously then, what is integration of tan x? So 6, integral tan x dx is integral sin x by cos x dx. But you know integration of cos is actually minus sign, so there is no minus sign here, so let's adjust one minus sign in and out. So minus ln mod cos x plus c, which is same as log mod secant x plus constant, because you know plus constant. Okay, because you know, like if there is a minus to the multiplication of log, this minus can be taken to the top here, okay, as a power to the cos x. So cos x whole power minus 1 gives you 1 by cos x, which is secant x. Clear? Then let's calculate integral cot x dx. So what is integral cot x dx? Integral cos by sin x dx, so which is equal to ln mod sin x plus constant, or which is minus ln mod cosecant x plus constant actually. Okay, so that's one integration. Then let's see integral secant x dx. So can someone tell me what is the value of this integral secant x dx? Any idea what we can do? Integral secant x dx. What is the value of integral secant x dx? No idea. So ln mod secant x plus tan x plus constant. Okay, so that's the integration. Like you can see how I would have got that. Integral secant x dx. Can I write this as integral secant x into secant x plus tan x by secant x plus tan x dx, of course, because I've just rationalized with secant x plus tan x. Now what is the integration of, sorry, what is the derivative of secant x actually? Derivative of secant x is secant x tan x, okay, and derivative of tan x is secant square x, you know. So the derivative of tan is secant multiplied with the secant, which is secant square x. Derivative of secant x is secant multiplied with tan, we have secant x tan x. So now in such case, this numerator is exact differentiation of this denominator function, so ultimately this value is going to be ln mod secant x plus tan x plus constant. Okay, so that's one of the integrations. Okay, then let's see 9, integral cosecant x dx. So this you can do by yourself, I'm just giving the formula. Cosecant x minus cot x plus constant. Okay, because ultimately like this, if you manipulate with cosecant x minus cot x, in this case you will see the denominator is exactly the numerator is exact derivative of this function, so you will get log mod cosecant x minus cot x. Okay, then let's see, then trigonometric functions got finished. Let's say exponential, you go to exponential a power x dx. Okay, so this gives you a power x by log a to the base e plus constant. Okay, so if you replace a with e, then this log e to the base e becomes 1, and integration of e power x is actually e power x, of course. E power x dx is e power x plus constant. Okay, so that's what you have. And so exponential functions got finished. So let's say log functions, or basically let's say f dash of x by square root of f of x dx. So if you have these functions, then ultimately this is 2 times root f of x plus c. That's the integration, because again if you differentiate this, you will end up with this. Like you can see d by dx of 2 times root f of x. So this gives you 2 can be taken out. So d by dx of root f of x is 1 by 2 root f of x into the function inside gives f dash of x. So this value is actually on the left hand side. Okay, so that's why integral f dash of x by root f of x dx gives you 2 times square root of f of x plus constant. Okay, then let's see other cases as well. So log cases you have seen. So let's say if you have log x. Okay, so integral log x to the, okay, this I'll teach after by parts, but in general you have so let's say, so trigonometric, algebraic, exponential. Okay, so log you can log and inverse trigonometric you can deal after integration by parts. Okay, so let's see, before that I would like to give few more things. 13 integral 1 by x square plus a square dx is actually 1 by a times tan inverse of x by a plus constant. Okay, so tan inverse of x by a plus constant again. Like you can see, if you replace x is equal to a tan theta, and if you straight away integrate this, you will end up with this function. Okay, so then 14 I would like to give integral 1 by a square minus x square d, or root of 1 by root of a square minus x square dx. So this gives you sine inverse x by a plus constant. Okay, so these two are a bit important again, they keep appearing very frequently when we are dealing with circles and things like that. So this is important again. So let's see the next sites. 𝐂𝐤𝐬𝐿 principle. Okay, and this 𝐂𝐤𝐬𝐿 principle tells you first of all integration by parts. Okay, so the principle that specifies the order of the functions, the order of the functions to be considered, that is to be considered during integration when you have multiple functions. Okay, so during integration actually, so during integration we have to consider the order. And how do we consider them? So let's say integration by parts. So basically this tells you 𝐂𝐤𝐬𝐿, the functions has to be arranged in this order, where I stands for inverse trigonometric. Okay, so I stands for inverse trigonometric functions. So when you are integrating product of two functions, it's always suggested to have this particular order so that integrations will become simple. Okay, so inverse trigonometric functions. Then L stands for logarithmic functions. A stands for algebraic functions, like normally polynomials, all these cases. So algebraic functions. T stands for trigonometric functions like sine, cos, all this. And ultimately the last type, E stands for exponential function. Exponential functions actually. Okay, so this is the 𝐂𝐤𝐿 principle, of course. And in this 𝐂𝐤𝐿, if you see the order in, if you have product of two functions, for example, like you can say in general, if you have integral e power x into x cube dx, okay, so then ultimately if you try to integrate in this order, okay, as it is, it gives you a lot of calculations, okay, but in fact if you swap these two functions, this can be written as x cube into e power x, the function doesn't change. But when you are doing by parts, by adjusting this function in this form will actually make your result to be simple a bit, okay, so which we'll again see during the course. So integration by parts, so let's see integration by parts, integration by parts. So basically you'll consider parts of the function and you will integrate, that's why. So integration by parts. So let's say if you have this product of functions, integral f of x times g of x dx, okay, so integral f of x g of x dx actually. So this can be written as f of x into integral g of x dx minus integral f dash of x into integral g of x dx to this whole dx, because you have to integrate this with respect to this integration. So this is how you get the expression for calculating the integral when you have product of the two functions actually, okay. If you have product of three functions, then what you can do, so let's say if I have something like f of x, g of x, h of x dx, then what you could do, see, you consider this to be some, say maybe some alpha of x actually, okay, some function. Then this is one function, this is the second function, you can apply here, but in place of g you will be having alphas. So when you have product of two functions here, again you will apply by parts for this particular integral and also this particular integral actually, okay. So that's basically the way to do. Now let's see, let us calculate certain functions actually, certain integrals. I would like to give one technique actually. So if you have integral u v dx, okay, where u comma v are functions of x alone, so where u comma v, u is function of x and v is also function of x, of course, okay. So some functions in terms of u and in terms of x, both are in terms of x, but they are differentiable functions, of course, okay, otherwise you cannot integrate. So this integration is actually something like this, u into v1 minus u dash v2 plus u double dash v3 plus u, sorry, minus u triple dash v4 plus and so on, okay. So this goes. What about these things? So u is u, of course, v1 is first integration of v with respect to x in general, okay, or you know, basically this un is nth derivative of u, nth derivative of u with respect to x, of course, and vn is basically nth integral or nth integration of v with respect to x, of course, here, okay. So when you do this sequence, ultimately this is the first function, then this is the integration of the first function, this is second function, I mean this is the first derivative of the first function, this is the second integration of the second function, and so on. Like why this formula is very helpful, I'll tell you. Look, let's say if you have a function integral, let's say you have two functions out of which one is algebraic function, for example, okay. So let's say you have e power 2x into x cube dx. So let's say you have this integration and you want to solve this integration, okay. So as per 𝐂𝐬𝐿 principle, first of all you adjust the order. So the functions here are exponential and algebraic. So as per 𝐂𝐿𝐿, algebraic should come first, so x cube into e power 2x dx. Now normally if you apply by parts, let's see what happens. So first function into integral of second function minus integral derivative of the first function into integral of the second function e power 2x by 2 dx. This is what you will get, yes or no? When you apply 𝐂𝐿𝐿 first time, then this is what you I mean if you apply integration by parts, this is the function, but again still you have the integral sign, so and it is product of two functions again, so you will apply again by parts for this function. So let's see, x cube e power 2x by 2 minus 3 by 2 I am taking out, so integral of x square e power 2x dx is what you will have actually, okay. So this tells you x cube e power 2x by 2 minus 3 by 2 times of integration of this first function, integration of second, minus integral derivative of the first function into integral of the second. Correct? So this complete, yes, of course we have written already. So this is what you will get. So if you simplify this a bit, this tells you x cube e power 2x by 2 minus this term gives you 3 by 4 x square e power 2x, then minus of minus plus 3 by 2 times of integral x into e power 2x dx. Okay, so this is again the integration. So again, if you do apply by parts, because it is again product of two functions, so this function gives you x cube e power 2x by 2 minus 3 by 4 x square e power 2x plus 3 by 2 times of first function into integration of second minus integral derivative of this x with respect to x is 1, integration of this e power 2x with respect to x is e power 2x by 2 dx, of course. Okay, and this integration of e power 2x by 2 is actually e power 2x by 4, right? Because integration of this e power 2x is e power 2x by 2, there is already one more 2 in the denominator, so total it turns up to be 4. So if you add the total expression, you have e power 2x dx is equal to x cube e power 2x by 2 minus 3 by 4 x square e power 2x plus, now this is 3 by 4 x e power 2x actually. Okay, so 2, right? Yeah, 3 by 4 into x e power 2x is what you have. Okay, then after plus into minus, minus 3 by 2 and there is a 4 here, so 3 by 8 times e power 2x plus some arbitrary constant. So this is the total value of the integral. Yes or no? Correct? So please type in the chat box if you want to calculate this integration. Then you can see this is the complete value of the integral of this function x cube e power 2x, and if you differentiate this complete function, you will end up with x cube e power 2x. Fine? Did you all understand? At each and every stage I have applied by parts. That's all. Okay, fine. Did you all understand the standard procedure for working out? Yeah, this playlist will cover in complete engineering mathematics, but over some period of time. Okay, so please type in the chat box, is this fine to each and every one of you? Then let's see if this is the value finally. Now let us take the advantage of this particular expansion, whatever I have given you. Okay, so and this expansion is helpful when one of the functions is algebraic. When you have x cube e power 2x dx, so let us treat this as u and this function as v, of course. Okay, now let us apply the classical way what I have taught. First function into the first integration of this e power 2x by 2 minus derivative of the first function, which is 3x square. This is the first derivative. The second integration of this is e power 2x by 4, correct? Because differentiation of this is 3x square, integration of this is e power 2x by 4, then plus derivative of 3x square 6x, integration of e power 2x by 4 e power 2x by 8 minus derivative of 6x 6, integration of this e power 2x by 16 plus derivative of 6 0. So from here every term is 0, so let's keep this as some arbitrary constant c. So if you simplify this result, let's see, 1 by 2 3 by 4 3 by 4 3 8, of course. Okay, so if you simplify, you get x cube e power 2x by 2 minus 3 by 4 x square e power 2x plus 3 by 4 x e power 2x minus 3 by 8 e power 2x plus constant, and this value and this expansion both are same actually, you can see. Okay, but in this case we have done a lot of calculations, but if you know this technique, then this integrals can be solved very easily like this. Okay, but one caution, these integrals are helpful only if one of the function is algebraic. Okay, the reason is, let's say for example I have some instead of x cube I have sin x here, then if I have sin x, this loop keeps repeating. Yes or no? So that's why it creates slight issue again. After some part again simplification and bringing back I, things like this will happen. So I'm stopping it at this point. Okay. So this is integration by parts. Now let's see. Let us continue the standard formulations. I've given you some 14 formulas. Oh no, yeah, 14. So let's start. 15th. Integral sine inverse x dx is equal to x times root of x into sine inverse x plus root of 1 minus x square plus constant actually here. Okay, so this is the integral of sine inverse x, of course. Okay, so how you get this? Let's see why by parts has to be understood to calculate this. Let's say if you have I as sine inverse x dx, okay, the integrating variable is with respect to x. Now I can write sine inverse x as integral sine inverse x into 1 dx, correct? So this one can be written as x power 0, so this can be treated as algebraic function or exponential e power 0 anything. So this can be treated as algebraic or exponential anything, but since this is the first function, it's inverse trigonometric. As per Eilert order, this has to be treated as my first function. Okay, so this can be written as sine inverse x into integration of second function minus integral derivative of sine inverse x. What is the derivative of sine inverse x? 1 by root of 1 minus x square into integral second function dx whole dx plus constant. Okay, that's what you have. So minus integral 1 by root of 1 minus x square, the derivative of the first function into integral of the second function dx plus constant. Now clearly this term gives you x. So which means this implies I is equal to integral sine inverse x dx, which is almost like this is again x. So x times sine inverse x, okay, minus, so this is x of course, so integral x by root of 1 minus x square dx plus constant. Okay, so this is what you get. Now how to calculate this integration? That's the main question. Okay, so the function inside the square root is 1 minus x square. So what is the derivative of this 1 minus x square actually? Can someone tell me? What would be the derivative of the function inside the square root, which is 1 minus x square, of course? What is the derivative of this function 1 minus x square with respect to x? Derivative of 1 minus x square is x, is it? What is the differentiation of 1 minus x square with respect to x? Minus 2x, right? But you don't have minus 2x here, because if you have minus 2x, it's like f dash of x by root f of x. So what we'll do, we'll make these manipulations. You make this plus and put this minus inside, but 1 2 is also missing, so 2 and 1 by 2, that's it. Okay, so if you do this, then this becomes x into sine inverse x plus x into sine inverse x plus half times of this is integral f dash of x by square root of f of x, so which is 2 into root f of x plus constant. So this plus root of 1 minus x square comes from this, of course. Okay, so that's basically the calculation. One integration which is again very helpful to you is, I'd like to give here 16 integral root of a square minus x square. Okay, this is very much useful because in polar coordinates everywhere we end up with these kind of integrals. Why we will see as we move on to Jacobians in multivariables. So root of a square minus x square dx. So the integration value of this is x by 2. Sorry, the integration value of this is x into x by 2 root of a square minus x square. This 2 will be there or not? That's the question. So let's see, x into root of a square minus x square is x into root of a square minus x square x by 2, let's say, okay, plus a square by 2 times sine inverse x by a plus constant actually. Okay, so this is x by 2 root of a square minus x square, yeah, 2, they will be 1 by 2 of course. Okay, so let's see how I can show this. Basically whenever you have root of a square minus x square, you can make substitutions. This is very much useful. Okay, many times later when I'm solving problems and all in applications of integration part, Whenever I see this, I'll directly write this. Okay, now I'm telling you how you'll get this. Okay, so solution in general, let I is equal to root a square minus x square dx. Okay, so let's make trigonometric substitution. You can take cos theta also, doesn't matter. So dx is equal to cos theta d theta, correct? Because if you differentiate both sides, d of x is equal to d of sin theta. So d of sin theta is cos theta into d theta, which is here. So if you put it back, therefore I is equal to integral a square minus a square sin square theta into a cos theta. I think x equal to a sin theta. Okay, so this a sin theta, so this is a cos theta d theta, of course. Okay, so root of a square minus a square sin square theta into dx value is a cos theta d theta, of course. So I is integral. So if you take square root of this, a square minus a square sin square theta, so if you take a square common, you have cos square theta, and a square root gives you a square cos square theta d theta, of course. Okay, now a square is just a constant, you can write it out. Integral cos square theta. So how you can manipulate cos square theta in order to get the values? You can write it as 1 plus cos 2 theta by 2 d theta, right? Because you know cos 2 theta is 2 cos square theta minus 1 or 1 minus 2 sin square theta. So this cos square can be written as 1 plus cos 2 theta by 2, of course. Okay, then ultimately this 2 can be taken out as constants. Integral of 1 with respect to theta. Okay, I'm writing directly. Integration of 1 with respect to theta is theta, plus integration of cos 2 theta is sin 2 theta by 2 plus some constant actually. Okay, so this is the integral. So if you simplify this, let's see what you will end up with. Therefore I is equal to a square by 2, it's common, into theta. So what is theta? Of course, so if x is equal to a sin theta, this tells you theta value is sin inverse x by a, of course. Okay, so this theta can be replaced with this sin inverse x by a plus sin 2 theta by 2. So what is sin 2 theta? 2 sin theta cos theta, right? So 2 theta, so sin theta is x by a. If sin theta is x by a, what is cos theta? Root of 1 minus x square by a square, that's it. Okay, by 2, of course. This is the value you get plus constant. So if you simplify this, you know this 2 and 2 gets cancelled, and this term if you simplify, you have I is equal to a square by 2 times sin inverse x by a plus, so a square by 2 into, so if you simplify this, x by a, and this term gives you root of a square minus x square by a plus constant. Then you have this a square will cancel up these two, then I is equal to, which is integral root of a square minus x square dx is given by, so this is the first term. If you take x by 2 times, did I put 2? Okay, fine, root a square minus x square plus the first term is a square by 2 times sin inverse x by a plus constant, of course. Okay, so this is fine, plus some arbitrary constant. Okay, why I have taught this integration is because normally when we go for applications part, these integrals keep coming very frequently, root of a square minus x square terms, normally when you're dealing with ellipse or circle, these kind of things. So that's why I've taught this integral. So whenever I see this integral, I'll just apply this and apply limits directly. Okay, there, fine. Okay, so 1/17th integral I would like to give. You can try this. Integral ln x dx is x into ln x minus 1 plus constant. That's it. Okay, so you can give this integration. You can try ln x into 1, take ln x as first function, 1 as second function, apply by parts, you'll get this. Okay, or sometimes this is also written as ln x by e, x into ln x by e, because this 1 can be written as ln e, ln x minus ln e can be written as ln x by e. So few times you'll also see this as, that's all. Okay, fine. So these are some definite some integrals, of course not definite, indefinite integrals. We'll see the properties hopefully in the tomorrow's class. Okay, and then once we see the properties, then we will slowly move on to the applications part. Fine, because it's already 8:30, the time is up. We'll stop here for today. I had given a lot of information for today, but this is again a bit of useful information, so please keep this. And you can solve. Okay, since I didn't teach you definite integrals, we'll teach this. But in general, if you know how to solve definite integrals, this question I'm giving as homework, which can solve for tomorrow. Okay, and so in today's class we focused on fundamental theorems, of integration, like the fundamental theorem, then mean value theorem, and then Newton-Leibniz rule. Then we also focused on some standard integrals. So these are the things we have seen. So in tomorrow's class, we'll focus on the other, or basically some more, indefinite integrals are there. I'll give you those formulas, and then I'll apply properties of definite integrals to solve many questions actually. Okay, so we'll look at these things in tomorrow's class, and of course the tomorrow class timing is again at 7 p.m. So we'll start the class at 7 p.m. sharp. So please do attend. Don't miss the continuity. Okay, so please attend continuously so that you can have some enough idea, and that's all. If you have anything to ask, you can tell me. Telegram channel name. So these are the Telegram channel QR codes. If you just scan this, it directly leads you to the Telegram channel of mine, and this is regarding the English Telegram channel, so that any update on this English YouTube channel will be posted here. Okay, any doubts? Are you all understanding? I know I'm going a bit fast because this is all a bit of basic understanding of integrals, limits, which you have done in maybe +1 or +2 classes, and in your BTech you might have done, of course. So I'm just going a bit quick, but once we enter multivariable calculus, I'll slightly slow down the things and go in a organized way. Okay, but here, even if you don't understand something, please ask me. I'll stop and I'll go slowly. Okay, as I told you in the beginning of 1.0 lectures, in my class, if you have any doubt, it doesn't matter how small the doubt is, you can ask me all. Okay, so feel free to ask questions and learn things. Okay, fine. Okay, so if you have any questions, you can ask me, or else we'll wind up because it's already 8:30. I think time has flown very fast today. And okay, fine. So thank you all. We'll meet tomorrow at 7 p.m. Okay, so thank you. Yeah, take care. Bye.